we start looking at the electron and seeing why we're so worried about it. Quantum theory and atomic structure. Visible light is a type of EM radiation. Okay, it's composed of two things: electro and magnetic. They move perpendicular to each other. Okay, all waves are made up of the same kind of thing: frequency, wavelength, and amplitude. Frequency, we know, is the number of times something passes a certain point per second. A wavelength is the distance between one part of a wave to a matching part of a wave. If we can go crest to crest, trough to trough, usually the way that I do it. And amplitude, we're not worried about. It's the height from the center part, imaginary line, the center of the wave to the top or to the bottom. All EM waves move at the exact same speed, which is the speed of light. That's a constant in a vacuum, right? 3.0 times 10 to the 8 meters per second in the vacuum. And speed of light is equal to wavelength times frequency, because technically, speed of any wave is equal to its wavelength times its frequency. Because frequency, we measure it in per seconds, and wavelength measure it in distance. So distance divided by per second basically is a speed. We have three different waves we're looking at here. The blue wave has the highest frequency, so therefore it has the shortest wavelength. And that's the relationship. It's an inverse relationship between the two. As the wavelength gets longer, the frequency gets smaller. Okay, and this is just a general map of the EM spectrum. We can see gamma radiation as high frequency. We know there's high energy waves. X-rays are high energy waves, so they have a high frequency. On the other hand, radio waves, microwaves, they tend to have a lower frequency. And actually, this is a little bit too large what it has here for the visible light. But its range is between 400 nanometers to 750 nanometers. Okay, with the red being the low energy type and the violet being the high energy type. And this is what your eyes are accustomed to on this planet. So that's usually what our sun is giving down in the greatest quantity. Okay, so when we look at waves and particles, we can see that a wave, right, kind of refracts, kind of gets messed up when it enters from one medium to another. We know that water is closer together, much more dense than air, so it kind of changes the way the wave moves, and the same thing with the particle, does the same kind of stuff. But when we look at them as something going through a slit, waves go through what happens in C. And then particles, right, go through which happens in B. So the two main things you're looking at is wave, which is energy, and particles, which is matter. Okay? When we get a diffraction grating, when we have the light going through or energy going through, okay, so all objects have some level of frequency and wavelength. When they're heated to 1,000 Kelvin, it shows. It's called black body radiation. Okay, so it changes the light color. The light changes as the temperature changes. So the energy in the actual in the light changes as the temperature changes. And color is related to wavelength and frequency. Temperature is related to energy. Okay, and energy is equal to NHV. Really, the big important thing there is energy and frequency are directly related. H is Planck's constant, 6.63 times 10 to the negative 34 joules times seconds. You don't need to know that, though. In the end, doesn't matter as much in this scenario. Not yet. Okay, but what's important is that the energy and the frequency are directly related. So therefore, the energy and the wavelength are inversely proportional because frequency and wavelength are inversely proportional. Examples of black body radiation. Okay, any object can absorb or emit certain specific quantities of energy. That's the word they're missing there, it's specific. And it's based on where the electron's located, but we'll talk about that later. Okay, it's quantized, which means it's a fixed quantity. It's the exact amount that you need. It's not continuous like the spectrum of light you would see from violet to red. There are blips and stuff inside there, missing pieces of it inside of it, right? And each little space between each blank space is called a quantum. It's the energy needed to go from one blank space to the other blank space. Okay? And again, now the N means something here, right? Because N stands for the energy level. It can only be a whole number. Starts at 1. Okay, the line spectrum of hydrogen. Now, hydrogen is a unique element because it only has one electron. So it's probably the easiest element to study because it's so small. Okay, and so what happens with hydrogen is we'll see this with the gas tube. It'll produce the spectrum, this EM spectrum up on top, emission spectrum. So that means energy is being given off. We'll explain why it gives in a second. But it gives off its own specific colors of light. And we can use those specific colors or those specific wavelengths of light to determine what element we have. It's a fingerprint for hydrogen. Look on the bottom, we can see the fingerprint for mercury, the fingerprint for strontium. But that's where the lines come up. It's where the electrons are dropping. Okay, they get excited to higher energy levels and drop down to lower energy levels, which we'll talk about in a second. Right? And this is the way to calculate the exact wavelength that we would need as we go through. R is Rydberg's constant. The funky looking Y, upside down Y, is the wavelength. And the N are the energy the levels they drop from. It goes from one to the other. Drops from whatever N2 is into N1. So Bohr's model of the atom had it very specific where the electrons were located. There was no place in between they could exist. They either be at one line or the next line, kind of like climbing upstairs. Okay, and the farther the actual electron goes from the nucleus, the farther the energy level is from the nucleus, the higher the energy is. Okay, and when it's in its closest to the nucleus phase, it's called the ground state. Right. And when it's not in its closest to the nucleus stage, it's called its excited state. Okay? And the circular orbit is three-dimensional. It's not limited like a planet where it goes on a plane. It goes in every direction. Okay, and so in order to go ahead and give off energy, it has to absorb energy. And there's lots of ways they can do it. The easiest way is shine light on it. It's called the photoelectric effect. Right? And the electrons gain energy and they jump up. But it also can be done with electricity. It can be done with heat. Any way we can add energy to it, it'll force the electron to go up and go into its excited state. Okay? When it's in an excited state, it doesn't want to be there because we know that everything in the universe wants to go from high potential energy to low potential energy. So it'll emit a photon, a specific quantity of light to go down. So it absorbs a specific quantity to go up and has to emit the exact same quantity to go down. There's no in between with these. And we show it here. This is a classic example. Again, this one might have been in the film clips where the difference is in the energy levels. N1, the big drop is between N2 and N1. They try and make it out to be like a staircase. So as you walk upstairs, right, what's happening is each stair is getting shorter as you go up because it takes less energy to go up to the next level. The biggest drop is always going to be from the second energy level to the first energy level. And here we have Bohr's explanation of it dropping from different places. So the important thing is not necessarily that it's called the Bashel or the Palmer series, or whatever you might want to call it. What matters is that it's dropping to different levels. So the first one, the ultraviolet series, is a big drop. Because as we saw before, and we can see on the right-hand side, the biggest difference is between the second energy level and the first energy level. So that should correspond to the higher energy of light. And since the drop is so great, drop into the first, any time an electron drops from a higher energy level to the first, it always gives off ultraviolet radiation. You can't see it. It's too far past your eyesight, right? But then when it drops into the second, well, that's what your eye is basically set up for. To see those colors of light, and we can see in the visible series N1 equals 2, we can see that it's giving off red, funky shade of blue, blue, and violet, okay? And so when it matches up with the actual diagram on the right, we can see this they're all dropping in the second. And your eye, basically, anytime you see any of these emission spectrums, there are electrons dropping from a higher energy level into the second energy level. And then after that, the levels get too close together. So we can see that on the right-hand side, where the levels are too close together. So the energy they produce is very small, smaller than red, which would make it infrared. And we can see on the bottom, all the lines match up with the emission spectrum. That's what you see in the emission spectrum, the energy emitted when it goes and drops to a specific energy level, quantized. Okay, emission and absorption spectrum for sodium atoms. Okay, so the emission is the one we're used to. It's the electron dropping into a certain level, and you can see that's generated when it drops into the second. Okay, the absorption is just the opposite. You see everything but. It's everything but. Okay, and we have a spectrometer. Couple of cheapies, but they work, and they have a grating that actually goes through, and we'll be able to split light in our actual spectrometer and see different things. Okay, well, the wave-particle duality of matter and energy. I usually apply this to light, and essentially what we're seeing here is that light behaves like a wave most of the time, right? But it also behaves like a particle, which is crazy because in the beginning of any kind of science class that deals with physical science, we always say that chemistry is studying matter, physics is studying energy, and they don't cross. The problem is we went ahead and started taking the matter, making it smaller and smaller and smaller, and studying it. It started to show wave-like properties. So if we take light and we test it to see if it behaves like light, it does. Then if we take light and test it to see if it behaves like matter, it does as well. So that means it's duality. It behaves both as energy and both as matter. And the larger the mass, okay, the less it's going to show its wave-like properties. So human beings have wave-like properties, but you're massive compared to an electron. So there you don't see yours, but since the electron's so small, you can see it exhibits its wave-like properties. Okay? Every matter exhibits both. And there's our relationship underneath. H is again Planck's constant. And this is just showing how we go ahead and get wavelengths. Okay, and now we look at certain particles, how fast they're moving compared to their speed. Smaller they should be, right? The faster they should move or be able to move. Oh, that's not necessarily true of everything here, but the wavelength should correspond to it. So let's do it this way. The smaller the wave, the smaller the mass, okay, the smaller the wavelength. Okay. Essentially the same kind of stuff we're looking at, right? Photoelectric effect we saw was due to Einstein. Black body radiation is when you heat up your stove and it gets real hot. It's quantized. Only certain values are being given off. It's with the electron moving. And we've applied that energy is quantized to Bohr's model of the atom, which says electrons are quantized. And they can change orbit if they need specific amounts of energy to do so. Okay, all matter travels in waves. That's what we just saw with de Broglie. And mass and energy are equivalent. E equals mc squared. We don't need that though. We don't need it though. The Heisenberg-Uncertainty principle, basically, as we study electrons, it makes it difficult because electrons moving at very high speeds. So the issue is that you can know the location of an electron, but you can't know its speed when you know its location. And when you know its location, when you know its speed, you can't know its location. Okay, and that's what the relationship is here. X is the displacement, m is the mass, and delta U is the speed, right? Momentum. Okay. Again, more stuff we don't really need to know, but we switched our model of the atom, the quantum mechanical, because it's not Bohr's or it's specific anymore. We're worried about probability. We're most likely to find an electron. Electrons can exist all over the place. They're moving at super high speed in a very small space. They can appear to be everywhere at a given moment in time because of that. I think they're like a third or half the speed of light. I can't remember the exact number. So when we talk about measuring the atom now, we're worried about where it's most likely to find it. And that's where Schrodinger comes into play. He has an equation we're really not going to use, right? Talks about wave functions, which we're not going to deal with. And it gives us our first actual energy level for the hydrogen atom. It's in the ground state. And the two diagrams, A and B, show you where it's most likely to be, right? Most likely to be. And the other one shows you how we tend to draw it. It's what we call an S orbital, three-dimensional. That's why it's X, Y, and Z. Put the electrons everywhere at a given moment in time. And the darker the actual number of color, the more likely we're going to find it there. Okay, so what we're going to do is we're going to apply the quantum numbers to the electron. And to do that, we have to figure out why we need that. So the first thing we need to do is, if I can determine where the electron's most likely to be located, then I can use that information to see how the atom reacts or the element reacts. And so for me to go ahead and figure that out, the location of an electron, well, then I can go ahead and determine where it's located. And once I figure out where it's located, I can tell you how the atom should behave. As crazy as that sounds, right? So it's built off these first three quantum numbers. There's a fourth, which we'll get to later. Not necessarily worry about it as much. And they're based off each other. So we said the principal quantum number can be any whole number that starts with 1. It essentially is the rings around the outside of an atom in the Bohr model. The value 1, 2, 3, or 4 is about the size, right? How far is it away from the nucleus? Okay. The second one is all about what we call the shape of an orbital, right? The shape of an orbital, and our numbers can be n minus 1, so whatever n was. So if I said n is a positive integer, n is 2, then what I would do is substitute in where n minus 1 is located, an angular momentum quantum number, which is here, and then add 2 minus 1 all the way to 0. Okay? It indicates the shape. And the last one is built off n, and then we need this one to figure out the second quantum number, and then we need this one to figure out the third quantum number. So if I had 0 for my shape value here, then it would be negative 0 to positive 0, which is 0. And if I had 1, then it'd be negative 1, 0, and 1. That's how we do this. And it's the orientation. It's really what I like to say is it's the number of actual orbitals for that shape. That's the best way to say it. And here we've done some of the math. So we say the principal quantum number is 1. Then it's negative 1 to positive 1. Sorry, it's minus, we substitute the 1 in here, so 1 minus 1 is 0, so we get that value. Okay? And so therefore it only has 1 orbital. So don't think of these as numbers. Think of them as the number of orbitals. So then we'll do the next one. 2. Plug 2 in here. 2 minus 1 is 1, all the way to 0. So we have two numbers here, 0 and 1. And again, we go negative 0 to positive 0. And we go negative 1 to positive 1. So this shape here, we'll call it S, has 1 orbital. And this shape here, we'll call it P. So anytime we see a 1, it'll be a P. Anytime we see a 0, it'll be an S. And P has 3 orbitals. And then if we go to the third energy level, mind you, we're getting farther from the nucleus. We're going farther out from the actual nucleus, and farther out in the atom. We end up with the third energy level. Now we have these possible shapes. So it's bigger, so it can handle more. And we determine the number from plugging in 3 here. 3 minus 1 is 2. And then 1, and then 0. All the numbers in between is 0. And then this is an S. It has 1 orbital. This is a P. It has 1, 2, 3 orbitals. And this is a D. It has 1, 2, 3, 4, 5 orbitals. So this tells me the number of orbitals. This tells me the shape. And this tells me the energy level. And this is kind of a cross-cut structure of the S orbitals. And we can see the difference between a 1s and a 2s and a 3s. They're larger because it's farther from the outside, right? But it's just location and what probability we're going to find it most of the time. So it's kind of spherical. This is a P. They call them dumbbell shape, right? Dumbbell shape. And there's 3 of them. So we have all 3 sitting here, right? This is the PZ, which should be one of the PY and one of the PX. This is a D orbital. And we can see that we have, there should be way more than these, right? And they're not showing all of them. Maybe it's in the next one. Different kind of ways to stretch the electrons out to different places. There's a lot more than this. There they are. Let's see. So E, F, G, H, and I are all going to be the, D, E, F, G, H are going to be the orbitals for D. And then this is them arranged together. All right, and then the F orbitals. Okay, so they show the F, which we'll talk about too as well, but they don't show how they break them down. Okay, and this is how we show some of them the energy levels. We put 1s. The line represents the number of orbitals we have. We can tie it back to the diagram we saw before. It only has one S only has 1 orbital. S only has 1 orbital. S only has 1 orbital. No matter what number is in front of it, it only has one orbital. And we maintain the Bohr model where we look and see the distance between the energy levels gets smaller as you go out. The biggest drop is between 2 and 1. But now we have 2 shapes in the second one, right? And we have P's, and there's 3 orbitals there. And we have a 3p, but we don't have a 1p. It's not there, right? It's not allowed. But a 3p is. And there can be 2 electrons in each. And then a 3d. And then the next one will be 4s, 4p, 4d, and 4f. And then we can see if we can figure out the pattern. 1, 3, 5. All right, I'll leave that to you.